everyone. First of all, I would like to thank the organizers for this workshop. What I'm going to discuss today is mathematical questions in crystals. I'm not sure it's kind of related to geometry, but I'm not working on the geometry, so I apologize. I think it's kind of related to topology and geometry. And I realize this is good time to give some sort of introduction for liquid crystals, because as far as I know, in Japan, nobody working on, no mathematicians working on liquid crystals, although in physicists there are many people working on liquid crystals. Also in Korea, I'm the only one person who is working on liquid crystals. So first, so I will give this is the outline, and first I will give some. First two ones are first is overview, and then I give some mathematical description on liquid crystals, and I will give some basic introductions, and then we'll discuss interfaces problems and some questions that is relevant, related to the geology conjectures somehow. So I think most of people, I'm not sure you know liquid crystals. So some of you already know, haven't seen liquid crystals. Liquid crystal is actually the material, state of matter between liquid isotropic fluid and crystalline solid. So it both contains properties of liquid and solid. So it's a little bit complicated materials. And so this is actually the real picture. It's observed in the insect eyes. So that you can see little small faces. Those are symmetric. It's actually one of the liquid crystal face. So it's kind of focal conic faces. And this one is observed in the UPenn group, University of Pennsylvania physicist lab. They got this picture, and they actually produce this kind of structures in the lab. They put some colloid, big colloid inside, and then they actually produce this type of structures. And then they try, I think right now they try to use micro lenses using this kind of techniques. This is another picture I got from some chemistry workshop, and they actually put some. This is the liquid crystal inside here. This is the liquid crystals, and then on the surface they put some polymer. They attach the polymer, so the liquid crystal, direction of liquid crystal is actually perpendicular to the layer on the boundary. And they keep this one, and then they move it around, and then actually catch the breast cancer cells. So now this is kind of biological application, medical application of liquid crystals. And actually, recently, this year, I think April, actually in Caltech group, they found a existence of 3D quantum liquid crystals. That would be possible to use for quantum computers in the future, but they actually found this. So here is the very basic liquid crystal phase. So when you look at the isotropic fluid, this is isotropic fluid, and then when you look at the direction of molecules are random. So which means that when you pick one point and then you look at the very small neighborhood and then look at the average direction of molecules, if you sum them up, it becomes zero. So it would be isotropic. So when you lower temperature a little bit from isotropic phase, and locally molecules point in certain directions, preferred directions, and we are interested in only direction of molecules. So we represent direction as a unit vector at each point. So here, when you have omega, so actually the n is the function from omega to S2. So S2 is here. So already we have constraint magnitude of n equals to 1. And in this case, when you consider molecules are all rod-like means like rod, and which means rotational symmetry. Molecule has a rotational symmetry, then we represent a liquid crystal using n. And then one of very classical, the energy for liquid crystal is known as Ocean-Franck energies. So Ocean-Franck energies consist of several terms here, and this is a divergence n squared, and then this one is curl n dot curl n. This is a kind of related twist terms, and then this one is called the bending terms. So each term has physical meanings. So one term, one is a molecules trying to be like this, organized like this, and then twist the term, molecule trying to rotate like helical patterns, and then the last term is a bending term. They're trying to bend in this way. And then mathematically, what you for equilibrium state, you want to minimize this energy with among the functions n is omega 2 S2, and then these three terms are competing each other, and this one, these three, according to the coefficient, these three behaviors are competing each other in the minimum state. So this gives you already some complicated structures. And then this energy has been studied by many authors. I'm not going to discuss. This is actually kind of well studied. So these are the related. The regularity of minimizers are actually done by Schoen-Uhlenbeck. So the previous energy, for this energy, you consider K1, K2, K3 are all the same K. And then you consider K4 equals 0. K4 equals 0. And then the energy, F Ocean-Franck energy reduces just K and gradient squared. And then you actually minimize K gradient n squared. This is our energy. This is our energy, Ocean-Franck energy. And then you minimize this energy with the constraint n equals to 1, so you actually end up with the harmonic maps. So you got a plus n plus gradient n squared n equals to 0. So you got actually harmonic maps. So this is a harmonic map. Actually, the Schoen-Uhlenbeck, their series of papers, they studied the regularity of harmonic maps, and actually using this one, and they actually extended those regularity and existence actually done by Hart, Kindlerer, Lin, and they actually started in 1985. Actually, the variation of formulations started 1980s and then 1990s, 2000, and this energy has been well studied by now. Okay. And then I don't have pictures for this. And then the one other thing I want to remark is that if n is a minimizer, for Ocean-Frank energy, so the energy I mentioned before, Ocean-Frank energy, so we call this one. Even K1, K2 case is a different case. Minimize, and n allows for the singularities. And then singularities. Suppose x0. Suppose x0 is a singular point. Then you have omega. Omega is domain omega, and then I have x0. And then the behavior of the director field n around here is actually look like this way. Almost look like this. Here, around here actually look like this. Or you get the rotation matrix. So this is actually well studied by Nonlinear and Troyan, and actually people extended to the Ocean-Frank energies. And then for this case, if n allows for singularity and singular point are finite for this case. But in general, in Ocean-Frank energies, it is not known whether the singular point of minimize are finite or infinite. It could be infinity, but the Hausdorff measure for singular point is actually less than 1. So, but people, we don't know whether it is finite or not. That's one of the questions so far. So which means, so the important thing is if this one has a minimizer allows a singular point. Singular point actually looks like this. And then this one has degree. Topological degree has 1. Degree 1 singular point. So that's it for Ocean-Frank energy. This is already. And then these days in liquid crystal community, they don't really, they are not interested in this energy anymore. But analysis point of view, there might be some more analysis than to do. But somehow in physics, they have been observed different type of singular point. So you have, suppose you look at one point, and then this is our domain occupied by liquid crystal, and they actually observe a certain singular point. So singular points look like this. You look at any loop around this point, and then you look at the direction of molecules, and then here molecules point this direction when you look at M model, and then here molecule point this direction, and then come back the other side actually and point opposite direction, and then here maybe like this, here maybe like this, and then when you start this point, you turn around, you move along this way, and then N actually turn to 180 degrees. So actually this is N direction. Actually rotate N, rotate 180 degrees instead of pi, in 2 pi. They actually, and then when you look at along this line, you can see above this line and point this directions, below this line and point that directions. So when you look at the ocean-Frank energy, and we have a certain line, along this line, actually n jumps from one side to opposite directions. So suppose this is my L, and then when you integrate L, my gradient n, so actually it becomes infinity. So this type of singular point does not allow for ocean-Frank energies. Okay? So, but in the physics, they have been, this type of structures are observed. And in mathematicians, we try to understand how we capture these structures using PDE or variation using energy forms. And that's one of the reasons we are interested in the new model. It is called the Landau-Dejong model. So we are interested in Landau-Dejong theories.
To make it precise, so in this case, you assume the bound multiplies in the length circle. You assume prescribe the vectors, and then you have this kind of line singularity.
So if when you have n had this kind of structures, and then actually n jumps along this line, and the direction n jumps from here to here, so opposite directions.
Which means so this red circle, on this red circle, you prescribe the vector first, like boundary conditions.
It's not boundary conditions. It's sort of if you have these structures, then integral becomes infinity.
Okay.
And that allows so minimize n. So from this one, minimize n does not allow such singularity.
Yes.
That's what I'm trying to explain. But this is type of singularity appears in the nature. And then such a point here is called the one. This point x0 is we defined as a singular point with degree 1/2. So this is 1 degree 1/2. But you get using Landau-Dejong theory, you actually this point is not singular. This one is not singular line anymore. Using the Q tensor, we call Q tensor.
This new theory does not cover such kind.
Actually, this one actually cover previous ocean-Frank energy. Kind of extended the model. Yes. So here is the one. So suppose that omega is the domain in R3, and then x you take x1 point. I look at the we have omega and the 1 point, and then the molecule points all other directions. So and then we assume the molecules we don't distinguish head and tail. So head and tail the same is n equals minus n. Actually, the crystal model n equals minus n. They have the same energies. So n minus n. And then at each point, the probability of the direction of molecules, which is called f, is a probability. And it has a symmetric structures, f even functions, f minus l equals fl, because there's no head and tail. And then look at when you probability density, you look at the first moment, you actually becomes 0. So when you separate those spheres, the upper hemisphere and lower hemisphere, it has the same, f has the same kind of symmetry, and you actually becomes 0. And then I look at the second moment of the probability density, you got here L tensor L is 3 by 3 matrix. Li, Lj. I from 1 to 6, Ij. But this is 3 by 3 matrix. So this is 3 by 3 matrix, this scalar function. And when you look at m equals like this second moment, then you got the, because any unit vector, and then you look at the trace of this matrix becomes 1. And this is also symmetry matrix. Symmetry matrix. And then for isotropic case, isotropic phase, every direction has the same equal probability. So in that case, the constant probability, if f equals 1 over 4 pi, then you compute the second moment, that becomes 1/3 identity matrix. Just actually compute. And then we set Q equals m minus m0, m minus 1/3 identity matrix. So we call this is actually 3 by 3 matrix, and it is a symmetric, and then trace of this is 1, trace of this is 1, so trace of this matrix is 0. And this is called second moment. So this is actually distinct, to tell us the how far this material away from the isotropic. So this is what we call second order tensor, or Q tensor. And then using eigenvectors of Q, I can write down, write down Q matrix as M tensor M as 1 times M times M minus 1/3 identity matrix. And also and then we have this one. And these are the orthonormal basis consisting of eigenvectors. So when you write one of the advantages of using this, Q represent using eigenvectors you can actually compute eigenvalues very easily using S1 and S2. So you actually compute eigen. You apply m vector here, n vector here, m vector, and this becomes your this tensor notation V tensor W, and becomes W. I think you got this one. You have this, and you actually, when you apply this to n, then this term becomes 0. You can easily see that n is eigenvector. The same for m. These are eigenvectors. And a liquid crystal is uniaxial when 2 of eigenvalues are equal. So 2 of eigenvalues are equal. We call it liquid crystal is uniaxial. And then liquid crystal biaxial means Q has all 3 distinct eigenvalues. So if eigenvalues of Q are all distinct, we call biaxial. And then it's uniaxial. So when you look at, suppose one of S1 or S2 equals 0, that is actually the actual case. So when Q equals S times N times N minus 1/3 identity matrix. Then you can plug. And then you get, this is one is S1 equals 0. So we got S0, 0, 0. So you can easily see 2 eigenvalues equal. This is uniaxial. Okay. So using actual Landau-Dejang theory actually represent molecules using these Q tensors. And directional molecules are defined the largest, but the the unit vector corresponding to largest eigenvalues. Yeah. So that's the direction. And then classical, the Landau-Dujang energy is actually the phenomenological model describing state of nematic phase. So nematic means, we are just talking about nematics. Nematics, a molecule has only locally has prepared directions, so we call it nematic. And then when you define the energy must have a frame indifference. So frame indifference, and then this nematic has the n equals minus n. So finally we have, this is kind of O3 symmetric structures. So F, the energy must satisfy FQ gradient Q equals, for every rotation, R is an O3, and then you have you plug this one instead of this, and then here it's a little difficult. This is the third order tensor, defined to be like this. You plug in here, and this energy must satisfy these symmetric structures. The energy Q, and the F is the Q, gradient Q, and F. And then actually you can, but this is just the symmetric structures, and using algebra, you can actually separate the F energy as two parts. We call F elastic energy, and then F bulk energy. So this one involves Q and the gradient Q, and this is only involves with the Q. So basically, this one is you can actually using that structure. So this is actually a function of polynomial. So this is a function of trace Q squared and trace Q. So this is the function of these two variables. So this trace is exactly summation of this one has three eigenvalues. So you square eigenvalues and then sum them up. And this is exactly the same as I from 1 to n. You have eigenvalues Q. So the reason is trace Q equals 0 means summation eigenvalues are equals 0. So using this property, we actually get this. This bulk energy actually the function of trace Q squared and then trace square and Q. And this one involves the gradient of n. And you can, when you separate two functions, so you actually end up with this type of, this is elastic energy. So I'm using the Einstein conventional notations. So you have II double, JJ double, KK double, then you get actually summation. Or I from 1 to 3, J also from 1 to 3. And this is exactly gradient. I didn't explain. So when I say QI, JK means partial derivative QIJ respect to SK. So this comma K means partial derivative. So this all involves the gradient. And this one means this index comes the same. This is actually divergence Q terms. Divergence. You have Q matrix, and you can actually define the divergence Q. define divergence. Some books even some define the difference this one divergence of this vector, divergence of this vector, divergence of this vector. But we don't care because Q is symmetric. So some books use divergence of this vector, this vector. But in our case, either one is okay. So this is actually the divergence of Q terms. And then when you look at here, this is IK, JK change. This is more related to curl terms. So the curl, you can actually define curl of Q. This is the vector. Divergence of Q is also vector. And then this is the L4 terms. L4 terms is kind of related to Q, and then you have gradient. So this is actually very difficult terms to handle. And this is that we took only the simplest part. There are more terms, but this is the most important terms. And also the F bulk energy actually the function of a trace Q squared and trace Q cubed. So you have this type of functions. And then you have a more higher order polynomial in terms of these two. This is very classical the lambda two-Jang energies. And then for simplest case, when you consider Q equals S times n tensor minus 1/3 identity matrix, and then you compute all these 4 terms, you end up with the divergence n squared, n cross curl n. You have all these you can actually compute, and you actually end up with having this type of K1 gradient divergence and K2. This twisted term, this bending term. This is actually the Austen-Frank energy I introduced at the beginning. So this energy actually recover the classical Austen-Frank energies. So Austen-Frank energies, they only consider uniaxial, which means eigenvalues of Q, 2 of them are equal. That's the theory for Austen-Frank energies. And then, as I mentioned, the K4 term is a very bad term. If K4 is non-zero case, the energy is not bounded from below. You actually construct a sequence, the energy goes to minus infinity. So that actually the example was constructed by Jambol and Appala Majumdar when Appala was postdoctor of Jambol in Oxford, and they actually did construct a sequence that goes to minus infinity. And then when you look at when you want to study the existence of minimizer, you have an elastic energy term. To make sure this energy has a minimizer, we have some conditions on L1, L2, S3 terms. Although this is kind of bad terms, so most people consider L4 equals 0 to make sure it has a minimizer. So these are the conditions for existence minimizer. So when L4 equals 0, and then you can assume L1 is positive, and L1, L2, and L3 are positive. This one was assumed by, I think I switched this to Wei Wang and Ping Zhang's group, and then you can also assume L1, L2, S3, some are positive, L2 plus S3 negative. This is still okay. And then the other case, all 3 different cases are okay. This one was done by Gartland and Davis. So in that case, we have this kind of quarship. They have, make sure this one has a minimizer. So minimizer is fine. Existence minimizer is fine. And then you have a bulk energy. So for bulk energy, you can actually prove the absolute minimizer for bulk energy, absolute minimizer. absolute minute only for bulk energy has a uniaxial. So bulk energy, I gave you definition F bulk. So F bulk energy Q is simply A over 2 trace Q squared minus D over 3 trace QQ plus and the square. So you mostly we assume A is positive, B ABC. So both positive case. Then when you actually minimize of this, minimize on for only this part Q, we actually look like S n times n minus 1 to identity. This is uniaxial. This is uniaxial. So which means when you minimize this one plus elastic energy, the energy trying to be uniaxial. You mean the partial is trying to be uniaxial. It's more like you have Allen-Khan equation. Allen-Khan equation, you have a frame of interval lambda equations. U square minus 1 square minus 2 square domain. And you minimize this one, it's trying to be U equals 1 or minus 1. It's the same for this. This is the more generalized than this one. So this energy force Q to be uniaxial. Yeah. So then we want to know when you want to compute the S values, and then we know global minimizer for this one look like this. We plug this one into the energy, and then you actually get the 1/3 AS squared minus 2b over 27 S cubed, and this is just polynomial of degree 4. And then you have several cases, okay, for this polynomial. So how many cases do we have? According, there's a fourth order polynomial. So you have this is the S variable. This one is f above function of S. And then one case, you may have this type of graph, right? And then this graph will be becomes like this. You may have this one reflection point, and then you change some variables. You will get. This is S equals 0, and we have 2 local minimizers. And then at some point, you may have equal. This has equal local minimizers. You change the variables, you will actually end up with something like this. And then this 0 point becomes a reflection point, and then you have a local minimizers. You change the variable ABC. You have all different type of graphs. So when you want to study nematic liquid crystals, then this is the case. So this is the graph, okay, and this we call S plus. Okay. And then here there exists when there exists T star and T double star, and when T is less than T star, then isotropic state unstable, and nematic state global minimizer. That is the case. When you look at S equals 0, is also when the derivative becomes 0, and this one is global minimizer. This is local minimizer, and this is unstable. And then T star is between T and TC, then F bulk has still global minimizer at S plus, and the local minimizer at S equals 0, which means this case, when you have this graph. So at this point, with global minimizer, this has local minimizer. And then you have a certain value, and this is for global minimizer. And then T is greater than T double star, then that's only global minimizer at 0. S equals 0 is only the global minimizer. So when you want to study different, I think when you have isotropic, S equals 0 means isotropic state. S plus means a pure nematic state. So you want to study a mixture of isotropic and nematic. So you can study the range of this graph. But at the beginning we defined Q. At the beginning, you remember we defined Q as n tensor n Fn minus 1/3 identity matrix Fn is sigma n. The surface matrix. We define Q as integral form. And when you have this form, then you look at the eigenvalues. Eigenvalues of Q belongs to minus 1/3. Should be in this range because you can actually compute group. The eigenvalues of Q belongs to minus. Smallest eigenvalue is greater than minus or equals to minus 1/3. And but this information is missing when you minimize energy. So when we minimize the classical Ossin-Frank energy here we don't have any constraint for eigenvalues of Q. So we are kind of missing this information. This is actually physical properties. So this, when you minimize this lambda Dujang energies, we don't know whether the eigenvalues of minimizer belongs to this range. This kind of missing. So that's why we need to modify the original energy here. So that's the one work by Jumbo and Palamajunda also in 2009 and 10. And they actually consider entropy terms. So they put entropy energy and then you minimize this entropy among rho, satisfying, this is the probability density. And then whenever Q is given, you can find some rho satisfying this one. And there are many Q rows, you minimize this energy. And you put this one in the total energy, you minimize. And then what they observed here, I didn't write down here. So here they look at this is all margin energy. All margin energy is F omega, and then F elastic energy. This is our original elastic energy, and then they put the psi Q. Instead of a bulk energy, they use this energy. And then they proved that the minimizer, the energy, so when Q, smallest eigenvalues of Q, so smallest eigenvalue of Q goes to minus 1/3. Eigenvalues of Q minus eigenvalues of minus 1/3. This energy goes to infinity. So that this term actually prevents the Q having eigenvalues less than minus 1/3. This actually corrected the original deficiency of original Landau-Dujan energies.
So is it kind of penalty term to prevent?
Yeah, I think it's kind of penalty term to prevent. But the studying using the Euler-Lagrange equation using this energy is not easy. You can actually the corrective is kind of difficult to handle this energy. So when we study, this is a very complicated energy, and when you look at Euler-Lagrange equation, it becomes complicated, and we usually use variational forms. But somehow this is a very good term. Somehow it's very difficult to analyze. And then there is another group to modify the original Frank and Landau-Dujan energies. It's a group in Peking University, Ping-Wang Zhang's group. They did some different models, but I just use a very simplistic case. They're using a so-called Bingham closure. And using the Bingham closure means whenever you have a Q is given, you actually compute 3x3 matrix, which is symmetric. You can actually find the BQ, we call it BQ, 3x3 matrix. B came from Bingham's. You actually compute this. This is actually play a role of, this is actually the rho X I mentioned in the previous slide. And then whenever Q is given, I can find BQ. BQ also 3x3 matrix, traceable 0. And then they put, and then this is another method that they actually end up with having a bulk, instead of bulk energy, they have a Q and BQ, sort of this inner product. So you have two matrix, A is a trace of B transpose A. So this is the inner product of two matrices. So the energy actually the Q and then BQ. Whenever Q is 0, you have BQ. And they have a log CQ. So CQ define this one. And the minus a certain gamma gradient. This is a square root trace U square. Symmetry matrix. Okay. So they end up with getting this kind of term. They may have a sort of different, a little different type of form, but I simplify everything. And basically, you have elastic energy, and they have this actually play a role of bulk energy terms. And both energy, the minimizer, absolute minimizer for this one, still uniaxial. Yeah. We can prove absolute minimizer of this one is still uniaxial. And then the absolute minimizer of previous slide, this one, the absolute minimizer for this one is also uniaxial. So that actually extends the Landau-Dujan energy. And then when you consider both energy, both the modified energy, you look at the energy near isotropic nematic interface. So near Q equals 0, you actually get the both energy look like maybe A, B, C are different, but they both has this type of terms. It's kind of Taylor series. You look at Taylor series, and then you first a few terms becomes this one. You have more higher order terms. And this is actually recover the original Landau-Tuzang entities, this kind of modified entities. Oh, it's already. And then we look at the only, now it is reasonable to assume, consider F is, we have F is bulk energy and elastic energy. Finally, we are assuming L4 equals 0. And this one has a minimizer. When you assume certain conditions, L1, L2, L3 has minimizers. And what we are interested here, so I'm going to split this one. So we are interested here are interface problem between isotropic and nematic. So you have a domain, this is our liquid crystal domains, and then a certain area is isotropic, Q equals to 0, and then you have Q equals 0, certain area has Q equals pure. This area is pure nematic, so Q equals S n times n minus 1/3 identity. And then here is still liquid crystal, but this is not pure nematic. Here it's possible that the Q has 3 distinct eigenvalues between here. So we are interested in this isotropic and this area. Interface, this is actually interface. Interface. And then suppose this interface is very small. So this is very very small epsilon. And then you actually, magnify epsilon. You rescale, then you take epsilon goes to 0, and you will end up with. We did some scaling, and then you actually get so this is the whole domain R3, and then we assuming something else, and then we have the 1/6 gradient Q, and then have this is the L2 terms, and then bulk energy. So for simplicity, we assume A equals 1/3, B equals 3, C equals 1, so that we have this bulk energy has this profile. This is our epilogue. So F has an equal probability for S equals 0, isotropic, and then pure nematic. Yeah. So this is the domain that now is R3. And then when you assume A equals 1/3, B equals 3, C equals 1, then F0 equals 0. And then this here, pure nematic, n tends to n minus 1/3 R becomes also 0. We have this state here. And then one other thing we want to study is the role of L terms. So L equals 0, then you have only gradient terms. L equals non-zero, this is actually involves divergence of Q. This may play a role in the interface problems. And then for one-dimensional case, what happens is that this is actually the one-dimensional case. The L2 equals 0, and actually the Tuzang actually considered this type of problems, and we are consider the homeotropic. Homeotropic means this is Q equals 0. The molecules here nearby is kind of perpendicular to the layer. This is what we call it homeotropic boundary conditions. So near the boundary is perpendicular, and then near the boundary you have a parallel. So we call it planar boundary conditions. Okay. So when Tuzang projected this, you have interface and then nematic phase and isotropic. This kind of interface is actually stable, or this type of planar boundary conditions also stable. That's what Zhang predicted. So in his L2 equals 0 case. Yeah. But when his case, he didn't consider the biaxial regions. So these days they have been observed that in some cases you have a certain area interface. You have around here pure nematic. What I'm saying pure nematic is actually uniaxial, pure uniaxial. But interface here, between here, there's some region. Q has 3 distinct eigenvalues. This is one of the mathematical things we want to prove. So for one-dimensional case, we actually studied. So for one-dimensional case, so I cannot show. The time is already finished. So in one-dimensional case with Wei Wang and Ping-Yang Zhang and Jifei, we studied there exists the uniaxial equilibrium state for those energy, which is stable with the homeotropic anchoring. That's for L equals negative. So L2 equals negative. And then L is positive, then this is unstable solutions. So we prove this is unstable, but we don't know what would be unstable solutions. But we can actually get the numerical simulations. You can actually, in some area, in some region between these two areas, and eigenvalue have changed. So in the between here you have three eigenvalues all distinct. We observe that one, but we still have questions. That's, I think, finally we posted some many open questions in the paper. The last one is this one. So you have suppose you have all local minimizer of lambda to Zhang, such as lambda to Zhang energies. We want to know whether level set of each component is a hyperplane or not. So in our 1D problem, we are assuming this interface is flat, one-dimensional case flat, but in general, it's not flat, but you have a level set component of Q. It's a hyperplane or not. We don't know if it's true. So here we posted some of open questions, so you may help us for these problems. Okay. Thank you for your attention.